Lesson 4.3, Trigonometry Extended, the circular function. So our goal in this lesson is to be able to find a trig ratio of any unknown angle and the trig ratio of any known angle using the 16-point unit circle. The trig ratios that we've set up so far have all been restricted to acute angles, in other words, first quadrant angles. But there's no reason to restrict ourselves to acute first quadrant angles. What we're going to do in this lesson is learn that trigonometry can apply to an angle in any quadrant. And it can apply to angles that are of any size. They can be any size in the positive direction and any size in the negative direction. So we're going to start with setting up ratios where we actually don't know what the angle is, because it's not the angle that we really need to know, it's the ratio of the sides that we need to know. And then we're going to look at situations where I do know the angle, but it's only going to be a certain set of special angles using that 16-point unit circle that we talked about in the last lesson. So let's start with trig of any angle of any unknown angle. So we're going to use concepts of right triangle trigonometry to set up trig ratios when I don't know the angle, which is the same thing I did at the very beginning of lesson 1. I would give you a triangle and then we would simply set up the trig ratios based on an angle, but never actually knowing what that angle was. Now, of course, we could use inverse trigonometry to figure out what the angle is using our calculator, but that's not what's important. What I want to be able to do is set up ratios. So imagine I give you a coordinate, and that coordinate could be in any quadrant. A coordinate is always made up of two values, an x value and a y value. Now that coordinate lies on the terminal side of an angle. So in this case, the angle theta would be starting at the positive x-axis and going counterclockwise to the terminal side, which in this case happens to be in the second quadrant. Now, based on our right triangle trigonometry that we learned in the first lesson, I would have no idea what to do to set up a trig ratio of this particular angle, because there's no triangle where I could define an opposite side, an adjacent side, and a hypotenuse. Or is there? Remember, trigonometry is based on right triangles, and right triangles can always be found by using the x-axis. Always remember that we measure our angles with respect to the x-axis. Now, generally, they're measured with the positive y-axis, but on occasion it can be useful to measure with respect to the negative x-axis. In this case, we're going to create what's called a reference triangle. We're going to set up our trig ratios not based on this angle, but based on this angle right here. We call that a reference angle because it's in our reference triangle. We need a right triangle to use to set up our trig ratios. Well, there's a right triangle right here, so that's what I'm going to do. Now, please don't make the mistake of creating your triangle with respect to the y-axis. It's always with respect to the x-axis. That way our angle is always the same angle from person to person to person to person. If some of you do it with respect to the x-axis and others do it with respect to the y-axis, well, then the math just doesn't work out. So if you're in any other quadrant other than the first quadrant where the triangle is kind of implied for you, just create your third side by connecting the terminal side of your angle to the x-axis, either by, if you're in the second quadrant, dropping it down, or if you're in the third or fourth quadrant, basically drawing it up, always to the x-axis. So if I have the coordinate xy, which is somewhere along that terminal side of the angle, then that xy actually tells me two things. It tells me two sides of the triangle, because x is simply the distance along the x-axis, and y is the distance along the y-axis. Now, in this case, since we're in the second quadrant, the x value would have to be negative and the y value would have to be positive, but that's perfectly fine. We can have trig ratios that are negative. There's no reason we can't. It's only in the first quadrant that everything stays positive. So just like an angle, which is allowed to be negative now, trig ratios can be negative as well. And the combinations of positives and negatives also tell you which quadrant you're in. If the x is negative and the y is positive, I'm in the second quadrant. Vice versa, I'd be in the fourth quadrant. If both are negative, I'm in the third quadrant. So we have to pay attention to positive and negative because it also tells me location of the angle. Now, if we have x and y for the sides, we also need a name for the hypotenuse. Of course, it has a name. The name is the hypotenuse. But what we're going to start to see is that trigonometry is directly related to circles, hence the name of the section, the circular function. Instead of calling the hypotenuse, let's keep with the theme of circles and throw in some circle terminology. Let's call the hypotenuse the radius. Because imagine you have a circle where the origin would be the center and then xy would be a coordinate on that circle. Then r is the radius between the center and some point on that big circle. And of course r, by using the Pythagorean theorem, can be found simply by doing the square root of x squared plus y squared. Now, by calling the three sides of the right triangle x, y, and r, this allows me to slightly redefine my trig definitions. Instead of using the terminology opposite, adjacent, and hypotenuse, we can say x is the adjacent side, y is the opposite side, r is the hypotenuse. So my trig ratios actually become a little bit simpler in order at least to write them down. I don't have to say sine of theta is equal to opposite over hypotenuse. I can say sine of theta is equal to y over r. Cosine is x over r, tangent is y over x, cosecant is r over y, secant is r over x, cotangent is x over y. So it's still the same old trig definitions, we're just using a slightly different vocabulary. We're kind of simplifying things, in my opinion. So instead of saying opposite, I say y. Instead of saying adjacent, I say x. Instead of saying hypotenuse, I say r. So let's use that concept to answer some questions. So let's start with basically the same way we started in section 1, by setting up all 6 trig ratios. So let's find all 6 trig functions of theta if theta is an angle in standard position whose terminal side contains the point 2, -3. So in this situation, I'm not giving you a triangle and finding all 6 trig ratios. I'm giving you a coordinate that you can use to build a triangle and then find all 6 trig ratios. So let's look at with this one together, and then I'll give you the next couple on your own. So the first thing I need to do is figure out which quadrant I'm in. Well, the coordinate 2, -3 is obviously in quadrant 4. So I can draw an angle in quadrant 4. Now I'm not going to really waste any time putting any tick marks on my x and y axes to represent a scale. I'm just going to say some arbitrary point on this angle, on the terminal side of this angle, is going to represent the coordinate 2, -3, and then draw my triangle, remember, always with respect to the x-axis. So I'm not going to draw my triangle this way, I'm going to draw my triangle this way. So that creates my reference angle, and since the x value is 2, I know this side would have to be 2, the y value is -3, so this side would have to be -3. Remember that x always represents my adjacent side, y always represents the opposite side. Now, of course, the only thing I have to find is the radius simply by doing the Pythagorean theorem. This is not one of my special triangles, so it's just going to be 2 squared plus -3 squared, so 4 plus 9, which is 13, so my radius would be square root of 13. Now, just like section 1, let's set up our trig ratios, starting with sine, cosine, and tangent. Now, keep in mind, the opposite side, the y value, is negative. Don't ignore the negative. The negative is just as important as the 3 is. So when I set up my sine ratio, normally I would say sine is opposite over hypotenuse, but using my new definition, I can simply say sine is y over r. The y value is -3, the r value is root 13, so -3 over root 13. We can leave it like this if it's a free response answer. If it's multiple choice, I'm probably going to have to rationalize it, so -3 root 13 over 13. Cosine is x over r, x is 2, r is root 13, so 2 over root 13 or 2 root 13 over 13. Tangent is y over x, opposite over adjacent, so -3 over 2. To get cosecant, secant, and cotangent, let's just take these 3 and flip them upside down. So remember, I'm not going to waste time with these rationalized versions. I'm going to take the unrationalized versions and flip them upside down. So when I flip them upside down, I'll get negative root 13 over 3, root 13 over 2, and negative 2/3. All right, here are 2 more. Why don't you give these a try, hit play when you're ready. All right, so let's look at -5, -12. And the beauty of this coordinate system, now I'm probably guessing that you do a triangle just like I did on part A, but I'm actually not even going to waste my time with that triangle. Since I know my definitions very clearly, sine is y over r, cosine is x over r, tangent is y over x, and so on, I'm just following a formula. As long as I know what x, y, and r are, then it's simply plug and chug. I know x is -5, y is -12. I can figure out r by doing the Pythagorean theorem or simply recognizing that this is a 5, 12, 13 triangle. As long as I have x, y, and r, it's simply a matter of writing down your ratios. Sine is y over r, cosine is x over r, tangent is y over x. Cosecant, secant, and cotangent are just flip, flip, flip. So if you want to draw a triangle, you're perfectly fine to draw a triangle. I'm not going to stop you from drawing a triangle, but keep in mind, you don't really have to draw a triangle, you just have to know the rules. So keeping that in mind, let's look at this one now. This is a situation where even if I wanted to draw a triangle, I couldn't draw a triangle. 1, 0 is already on the x-axis. There's no height, there's no opposite side to draw. So based on right triangle trigonometry, this question makes no sense. That's the beauty of the circular function. By thinking of trig in terms of a unit circle or within a coordinate plane, we can kind of ignore the restrictions that we had with right triangle trigonometry, and we are now able to answer questions that we could not answer back in geometry. As long as we know that x is 1, y is 0, and r is the square root of 1 squared plus 0 squared, or 1, then I can set up my trig ratios just like I did before. So sine is y over r, 0 over 1, which is 0. Cosine is x over r, so 1 over 1, which is 1. And tangent is y over x, so that would just be 0. To get cosecant, secant, and cotangent, I could flip, 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 but this is probably one of the points where you may or may not get a little bit confused. How do you flip 0? Well, remember, all of these are 0 over 1, 1 over 1, 0 over 1. So when I flip them, 0 over 1 becomes 1 over 0. But of course, you can't have 0 on the bottom, so it's undefined. Cosecant on this problem is undefined. Yes, you can have trig ratios that are undefined. That's perfectly fine. It is what it is. So cosine is 1, so secant would also be 1. Tangent is 0. Flip it upside down. Cotangent would be undefined. So let's take a second look at our understanding of when a trig function is positive and when a trig function is negative. By knowing when trig functions are positive and negative, not only can it save us time down the road, because I don't have to worry about remembering to put positive 3 or negative 2, because I'll know based on what quadrant I'm in whether the answer is going to be positive or negative. It will also allow me to narrow down. If I happen to know that a sine ratio is positive and a cosine ratio is negative, then I would automatically know that I am in the second quadrant as opposed to the first, third, or fourth quadrant. Now, the way I know that is simply by knowing how quadrants work. This is the y-axis. This is the x-axis. Positive y goes up, negative y goes down. Positive x goes right, negative x goes left. Now remember, the r value is found by using the Pythagorean theorem. R is defined to be the square root of x squared plus y squared. No matter what x and y are, R is always going to be a positive number. So we can kind of ignore the sign for R. The sign only applies, the SIGN sign only applies to x and y. So, first question, where are sine and cosecant positive? Well, sine and cosecant are defined purely in terms of y and r. R is always positive, so the only way for sine and cosecant to be positive is if y is also positive, because if y is negative, a negative over a positive would be negative. So if y is positive, then sine is positive. If y is positive, then cosecant is positive. So where is y positive? Y is positive anywhere above the x-axis. So anywhere up in quadrants 1 or 2 would be a positive value for y, and thus a positive value for sine or cosecant. If I'm in the third or the fourth quadrant, y would be negative, so sine and cosecant would be negative. So sine and cosecant are only positive in quadrants 1 and 2. Let's do the same thing for cosine and secant. Cosine and secant are defined in terms of x and r. X is positive anywhere to the right of the y-axis. So in other words, quadrants 1 and 4. So as long as I'm in quadrants 1 or 4, cosine is positive. If I'm in quadrants 2 or 3, cosine and secant are negative. And lastly, tangent, cotangent. So tangent and cotangent are defined in both terms of y and x. R doesn't play a role for tangent and cotangent. So in order for y over x or x over y to be positive, well, if both of the values are positive, like in the first quadrant where both x and y are positive, then y over x or x over y is positive. But of course, a positive over a positive is not the only way to get a positive answer. A negative over a negative will also give you a positive answer, and a double negative occurs only in the third quadrant. So tangent and cotangent are positive in quadrants 1 and 3, whereas they're negative in quadrants 2 and 4 because you'd have a mix and match of positives and negatives. So, in the first quadrant, we've seen that all 6 trig functions are positive. Everyone's positive in the first quadrant because x and y are both positive. That's why when we were doing right triangle trigonometry with acute angles meaning first quadrant, everything turned out positive. We never had any negatives because everyone's positive in the first quadrant. In the second quadrant, only sine and cosecant were positive. In the third quadrant, only tangent and cotangent were positive. Everyone else is negative. In the fourth quadrant, cosine and secant were positive. So everyone gets the first quadrant, and then everyone gets their own quadrant to themselves. Sine in the second quadrant, tangent in the third quadrant, cosine in the fourth quadrant. Now, there's a quick, easy way to keep this straight. First quadrant was everyone, so we say all. Second quadrant was sine, so we say S for sine. Of course, if sine is positive, cosecant kind of comes with it. Tangent for the third quadrant, cosine for the fourth quadrant. ASTC. All students take calculus. So as long as you remember ASTC, all students take calculus, then you can remember which trig functions are positive in which quadrant. Or of course, you could always go back to the definitions. Y is positive up here, y is negative down here. So sine is positive, sine is negative. Cosine is positive, cosine is negative. Because x is positive, x is negative. Tangent is only positive where the signs are the same for both x and y, so tangent would have to be positive in 1 and 3. Or all students take calculus. ASTC. So let's look at an example where that would be relevant. Let's evaluate just the specified ratios, cosine, tangent, and cosecant, where the sine ratio is 3/5, but the cosine is negative. Notice I'm not telling you what cosine is, I'm simply telling you that cosine is negative. So immediately, if I wanted to, I could put a negative on the answer for cosine. So let's look at this one together, and of course, I'll give you the next few on your own. So, just like we did in section 1, I can build a triangle whose sine is 3/5. The question is, which quadrant should I build that triangle in? Well, we can use these two pieces of information to help us determine which quadrant we're in. Now, right here it says sine is 3/5, but what it kind of really says is that sine is positive 3/5. In other words, sine is positive. So where is sine positive? Sine is positive in quadrants 1 and 2. Well, this statement says cosine has to be negative. Well, where is cosine negative? Cosine is positive in quadrants 1 and 4, therefore it's negative in quadrants 2 and 3. So we've got two statements. Where do they agree? Obviously, they agree in quadrant 2. So since sine is positive and cosine is negative, I must be in quadrant 2. Now that I know I'm in quadrant 2, I can go ahead and build my triangle. Sine is y over r, so the y side, the opposite side is 3. The r value, or the hypotenuse, is 5. So we can just find our third side using the Pythagorean theorem, or simply remembering, hey, 3, 4, 5, this is a 3, 4, 5 right triangle, so I can put a 4 down here. But of course, if I do, I'd be wrong, because this is not 4. This is in the second quadrant. The x value is negative, so negative 4. Make sure you are paying close attention to the sign. If you don't pay attention to the sign, you're going to get the wrong answer. So the x value is negative 4. Now I can go ahead and set up my ratios. Cosine is x over r, so negative 4 over 5. Notice it's negative, which is exactly what the given information said. Tangent is y over x, so 3 over negative 4, or negative 3/4. I'm in the second quadrant. My tangent ratio better be negative. And of course, cosecant, I don't need a triangle. Let's just take 3/5, flip it upside down, call it a day. So once you're done, double check your positives and negatives one more time. I'm in the second quadrant. Cosine is negative, tangent is negative, cosecant is positive. The signs make sense. Let's move on to the next one. So here's another one. Why don't you try this one on your own? Hit play when you're ready. So we've got tangent is negative 5/12. Sine is also negative. So I have a situation where both tangent is negative and sine is negative. So first thing I need to do is figure out which quadrant are both of these statements true. Tangent is negative in quadrants 2 and 4. Sine is negative in quadrants 3 and 4. So we've got agreement that we're in quadrant 4. We can build our triangle using the 5 over 12. But it's negative 5 over 12. So is it negative 5 over positive 12, or is it positive 5 over negative 12? Well, since I know I'm in the fourth quadrant, that answers my question. 5 is the y value, 12 is the x value. In the fourth quadrant, it's the y value that's negative. So it's the 5 that's negative, not the 12. So using my Pythagorean theorem, find the r, or of course 5, 12, 13, that's one of my Pythagorean triples, and set up my ratios. Sine would be negative 5 over 13, secant would be 13 over 12, cotangent would be 12 over negative 5. Alright, now we've talked about trig of unknown angles. Notice on all those previous problems, I never really actually cared what the angle value was, simply where the angle was located, and I set up my trig ratios based on right triangles. Now let's step forward and step back at the same time. Now I want to set up trig ratios where I know the angles, but I want to use special angles that I learned about way back in geometry. There were two special right triangles. The first one was the 45, 45, 90. The other one was 30, 60, 90. In the 45, 45, 90, we called it that because the acute angles were both 45, and of course the right angle is 90 degrees. So if this is 45 and 45, I have two angles that are congruent. That means I actually have two sides that are congruent. This is an isosceles right triangle. So if I have two sides that are congruent, let's just make up some arbitrary measurements because it really doesn't matter what numbers I pick. It's all going to reduce down to the same numbers anyway. So let's just go ahead and say it's 1 and 1. If the legs are 1 and 1, then the hypotenuse would have to be square root of 1 squared plus 1 squared, or square root of 2. So now that I know all three sides, I can set up all 6 trig functions. Notice I'm not using a theta anymore. I'm using 45 degrees because I know the angle is 45 degrees. So let's just go down the list. What's the sine of 45 degrees? Well, by using either angle, it really doesn't matter. The opposite side is 1. The hypotenuse is root 2. So I would have 1 over root 2. Of course, that would simplify to root 2 over 2. To do the cosine, I'm actually going to get the same answer because whether I use the opposite side of 1 or the adjacent side of 1, it's still 1, so I would again get root 2 over 2. So here's a special fact that we need to know from now on. Sine of 45 and cosine of 45 are equivalent. They are equal because they are both the square root of 2 over 2. And tangent of 45, one of my favorite ones because it's the one that's super easy, opposite over adjacent, 1 over 1 is just 1. So sine, cosine, and tangent of 45 degrees are root 2 over 2, root 2 over 2, and 1. And if I keep going to get the other three, cosecant, secant, and cotangent, I'm just going to take these three guys and flip them upside down. So root 2, and still 1. Cotangent and tangent would be just the same answer since it was 1. So we now have our 6 combinations, our 6 trig ratios at 45 degrees, root 2 over 2, root 2 over 2, 1, root 2, and 1. So as I said, 45 degrees is a very special angle. It comes up a lot. So because it comes up a lot, I don't want to have to draw this 45, 45, 90 triangle every single time it comes up. I want to just know that the sine of 45 degrees is root 2 over 2. It's not like it's going to change between today and tomorrow. Sine of 45 degrees has always and will always be the square root of 2 over 2. Therefore, memorize it. This list needs to be memorized. Now, the good thing about memorizing this list is even though there's 6 facts here, you only need to know 2 of them. Sine of 45 is root 2 over 2. Cosine of 45 is root 2 over 2. Tangent is sine divided by cosine. By knowing your tangent identities, and that sine divided by cosine gives you tangent, what's root 2 divided by root 2? Well, anything divided by itself is 1. And once I know those 3, flip them upside down to get the other 3. So as we go through this process, as long as you know the sine and cosine ratios, you really know all 6, as long as you also know your tangent identities and your reciprocal identities. So let's move on to the other special right triangle, the 30, 60, 90 right triangle. So obviously the 30, 60, 90 right triangle is so named because it has 3 angles. One is 30, one is 60, one is 90. So this one is just a generic right triangle. Nothing special about it other than the fact that the 2 acute angles, one is twice as much as the other, but other than that, nothing special about it. With the 45, 45, 90 right triangle, we were basing it on an isosceles right triangle, and thus we had a specific relationship between 2 of the sides that we had to start with. With this one, we do have a relationship because this is not the entire triangle that we're basing 30, 60, 90 on. It's actually an equilateral triangle that we base 30, 60, 90 on. 30, 60, 90 is really just half of an equilateral triangle. So just like with the isosceles triangle, the 45, 45, 90, we arbitrarily decided that the 2 legs would be 1 because in the end, it's the ratios that matter, not the absolute value of the side. We'll do the same thing with this one. We will arbitrarily decide on a side length, but this time I'm not going to choose 1 as my side length. I'm going to choose 2 as my side length. Now, I could just as easily have chosen 1, but the numbers work out a little bit prettier if I choose 2, because what I'm going to do right off the bat is take my equilateral triangle and turn it back into a 30, 60, 90 by cutting it in half. In other words, if I just look at just this portion of the equilateral triangle, the hypotenuse is still 2, but this side down here, only half of it's left, so the short leg, as we call it, is just going to be 1. So I still have that 1 there, but I had to start with calling all the sides 2 so I could cut it in half and leave the short leg as 1. So now I have 2 sides. I have a hypotenuse, which is the length 2. The short leg is half of that length, which is 1. And then the third leg can be found using the Pythagorean theorem, and I get square root of 3. So here are the 3 special sides of the special right triangle, 30, 60, 90, 1, square root of 3, and 2. So just like we did before, let's set up our trig ratios starting with the 30-degree angle, and then we'll do it again with the 60-degree angle. Sine of 30, here's your 30-degree angle. Sine is opposite over hypotenuse, so sine of 30 is 1/2. Sine of 30 will always be 1/2. Sine of 30 has always been 1/2. Memorize that the sine of 30 degrees is 1/2. And for that matter, the cosine of 30 degrees, adjacent over hypotenuse, will always be the square root of 3 over 2. Cosine of 30 is root 3 over 2. Sine of 30 is 1/2. And tangent of 30, I could just say tangent of 30 is sine over cosine, so it's going to be 1/2 divided by root 3 over 2, in other words, 1 over root 3. Or I could look at the triangle, opposite over hypotenuse, 1 over root 3, which of course rationalizes to root 3 over 3. The tangent of 30 is root 3 over 3. Cosecant, secant, and cotangent we can get by flipping, flipping, and flipping. So cosecant is going to be 2. Secant is going to be 2 over root 3, or 2 root 3 over 3. And cotangent will be root 3. So here are your sine, cosine, tangent, cosecant, secant, and cotangent ratios for 30 degrees. Now let's do it again with the 60-degree angle. So with the 60-degree angle, now this is going to be the opposite side, and this will be the adjacent side. 2 will still be the hypotenuse. And I'm going to set up my ratios just like I did before, going 1 by 1 and getting all of the same answers, but in a slightly different order. So the relationship between 30 and 60, the numbers kind of flip-flop. Instead of sine of 30 being 1/2, it's the cosine of 60, which is 1/2. And instead of the cosine of 30 being root 3 over 2, it's the sine of 60 that's root 3 over 2. It's all the same numbers, they just reversed order, and the order in which they reverse is between a function and its cofunction. It's not that tangent and cosecant switched, it's tangent and cotangent that switched. It's because they are cofunctions that they switch, because 30 and 60 are complements, co-complements, that cofunctions switch sides. That's what co actually means. It is the complement of sine, the complement of secant, the complement of tangent. So if I change the angle for its complement, I'm also going to change the function for its complement as well. Sine of 30 is equal to cosine of 60. Oh, and of course, before I move on, the 1 over root 3 is equivalent to root 3 over 3, obviously. So now I have 3 completely separate lists of information: the 45-degree angles, the 30-degree angles, the 60-degree angles. I wish there was a more organized way for me to keep all of this information straight. Well, there is. That's what the unit circle is going to do for us. It's going to allow us to keep all of this information straight without having to remember 2 separate triangles or 3 completely separate pieces of information. And there's something else the unit circle does for us. It allows us to answer this question right here. Sine of 90 degrees. Well, if I try to use right triangle trigonometry, I might start with, well, here's a right triangle. 30, 60, 90. So if this is 90, sine is opposite over hypotenuse. Well, what's the opposite side? The opposite side of the 90-degree angle is the hypotenuse. So is the sine of 90 equivalent to hypotenuse over hypotenuse, 2 over 2, which is 1? Well, for that matter, what if it was cosine of 90? Well, cosine of 90 would be adjacent over hypotenuse. Well, which side is the adjacent? Is this the adjacent, or is this the adjacent? If this is the right angle, both of these could be the adjacent. Of course, the hypotenuse would be 2, so then is the cosine of 90 equivalent to 1/2 and root 3 over 2 at the same time? And for that matter, why did I choose this triangle and not the 45, 45, 90? So when we throw in a right angle, right triangle trigonometry does not work. Right triangle trigonometry only works for angles that are acute. So what do I do when angles are right or possibly obtuse? That's another reason the unit circle is going to be so much more efficient for us. So let's take a look. The unit circle. based on the equation x squared plus y squared equals 1, which, as you learned in Algebra 2, that's the equation of a circle. X minus h squared plus y minus k squared equals r squared. Since there's no h and k, we know our center is at the origin, and the radius would just be 1. So since this is a circle with radius 1, that means I have 4 coordinates that I know right off the bat. This coordinate right here would be 1, 0, this one 0, 1, negative 1, 0, and then 0, negative 1. Now because we are using something called the unit circle, the radius is 1, that's why we call it a unit circle. Since the radius is 1, unit means 1. We can take our 6 trig definitions and actually simplify it one step further. Of course, this only works for a unit circle situation. It doesn't always work because the radius doesn't have to be 1. It's just 1 based on the context that we're looking at. So if I go ahead and plug in 1 for all the r's, instead of saying sine is opposite over hypotenuse or saying sine is y over r, when we're talking about unit circle situations, sine is just y. It's the y value. It's the y coordinate of the angle that I'm looking at. Cosine is x, tangent is y over x, cosecant, secant, and cotangent are all the reciprocals. So all I have to do from this point forward is look to see what angle do I have on the unit circle, what is the coordinate that corresponds to that angle. If I want sine, I want the y coordinate, cosine is the x coordinate, and all the other 4 are just combinations of y and x. So what's the sine of 90 degrees? Well, 90 degrees is right here. The coordinate at 90 degrees is 0, 1, and since sine is the y value, the sine of 90 degrees is 1. Not because of any arbitrary right triangle that I chose to use, but because the unit circle tells me the sine of 90 degrees is 1. How about cosine of 90 degrees? I couldn't answer that one before, but now I can. Cosine of 90 degrees, cosine is the x coordinate, so that means cosine of 90 must be 0. And I can do that all the way around. No matter which angle I want, all I have to do is look at my unit circle, look at the coordinate for that angle value, and decide on my answer. So the question becomes, what are the coordinates? So let's take a look. Let's put all the pieces together, go through the entire 16-point unit circle, and identify what the coordinate is for each angle. Starting with 30 degrees. That first coordinate on the 16-point unit circle is a 30-degree angle. We're essentially going to use our 30, 60, 90 right triangle, because if this is 30 and this would have to be 90, that's going to be a 60-degree angle. So here's my short leg, here's my long leg, and here's my hypotenuse. The hypotenuse in this case would be 1. So what would the coordinate be? Well, I know a coordinate is made up of an x value and a y value, and I've already listed out all of the sines and cosines of 30 degrees and 60 degrees, so I simply have to look at that chart from before. What was the cosine of 30 degrees? Well, we figured out the cosine of 30 degrees was root 3 over 2, and for that matter, the sine of 30 degrees was 1/2. So now I have my coordinate. This coordinate is the coordinate for the unit circle at 30 degrees. So whenever I give you a question, what's the cosine of 30 degrees, I could go back to my 30, 60, 90 right triangle, or I can simply look at my unit circle. Cosine of 30 degrees, cosine is the x value, 30 degrees would be root 3 over 2. Always and forever. Next step would be the 45-degree angle. 45 for both sine and cosine is always the easy one to remember because they're both root 2 over 2. And then 60 degrees is just a matter of taking the 30-degree coordinate and reversing it, because the sine and cosine are reversed from each other. So instead of the cosine being root 3 over 2, it's 1/2. Instead of sine being 1/2, it's root 3 over 2. One way that always helped me remember that is 1/2 and root 3 over 2. 1/2 is the smaller number, root 3 over 2 is the bigger number. As I get higher on the circle, the y value gets bigger. As I get further out on the circle, like at the coordinate for 30 degrees, then the x value should be larger. So at this coordinate, the x value should be larger. At this value, the y value should be larger. So I know the root 3 over 2 was the x value on this one. It's the y value on this one. But that was before I realized what the pattern was. Once I realized what the pattern was, that trick kind of went out the door. Every single one of these coordinates follows a certain pattern. So let's see what that pattern is. Let's start by filling in all 5 coordinates with their angle values, first in degrees and radians, and then we'll look at the coordinates and actually see how they're all directly related to each other. So obviously we'll start at 0 degrees. Our next step is 30, 45, 60, and 90. Then again in radians, 0 radians, pi over 6, pi over 4, pi over 3, pi over 2. Again, the radian denominators have to decrease because when a fraction's denominator decreases, the fraction, the number overall, gets larger. Now let's look at the coordinates. And here's the pattern. root n over 2. Every single number and every single coordinate on the unit circle is written in this form, square root of n over 2, where n goes from 0 to 4. So if you don't remember the specific values, just draw out your unit circle, starting and ending at your quadrantals, which are usually super easy to remember. The first coordinate is 1, 0, the 90-degree coordinate is 0, 1, and then fill in the blanks in the middle. All of the blanks follow the form root n over 2. Even these numbers follow the form root n over 2. Let's start with the y values because I always like to start with the y values. So at this coordinate, the y value is 0. And what's going to happen, the y value, as I increase up the circle, the y value is going to get larger all the way up to 1. But again, it's always of this form. So I start with n equals 0. This is the square root of 0 over 2. Square root of 0 over 2 is really 0. The next step is n equals 1. What's the square root of 1 over 2? Well, that's 1/2. After n equals 1 comes n equals 2. Square root of 2 over 2. Can't be reduced, it's root 2 over 2. Then root 3 over 2. Then finally root 4 over 2, which is equivalent to 1. So all 5 of these numbers fit the form root n over 2. Root 0 over 2, root 1 over 2, root 2 over 2, root 3 over 2, root 4 over 2. To get the x values, or the cosine values, you do the same thing, just in reverse. We start at the top and work our way down. So root 0 over 2, root 1 over 2, root 2 over 2, root 3 over 2, root 4 over 2. All of the numbers are the exact same form, root n over 2, and they're absolutely positively always in order. Starting with 0 going up to 1, starting at 0 going down to 1. And here is my complete first quadrant of the 16-point unit circle. This is what needs to be memorized. You need to memorize this first quadrant. If you don't memorize any other part of the unit circle, which you also still need to do, the first quadrant of the unit circle is absolutely crucial, because once you get the first quadrant, the rest of the quadrants fall into place, because the only thing that's going to change from quadrant to quadrant is positives and negatives. So let's fill in our degrees. 90 becomes 120, 135, 150, 180. Pi over 2 goes to 2 pi over 3, 3 pi over 4, 5 pi over 6, and pi. And then the coordinates. Well, this coordinate and that coordinate are at the same height, so their y values are going to be the same. The x value, on the other hand, one's to the right, one's to the left, so it's just going to be negative. So it's the same values. The only changes is the x value. The x value is now negative, and that's going to be the case on all of these coordinates. The actual values are exactly the same. We're in the second quadrant, though, so the x values are negative. When we get to the third quadrant, let's fill in the degrees and the radians. We'll go ahead and go all the way through third and fourth quadrant. The only thing that's going to change again is positive and negatives. In the third quadrant, both x and y are negative. In the fourth quadrant, only the y value is negative. So I'm going to take all the same coordinates, filling them in. All the numbers stay the same. The only change is positives and negatives. So there it is, the complete 16-point unit circle in degrees, radians, and with coordinates given. This is going to be the key to everything that comes further in your trigonometry course. You cannot understand anything that comes after this until you know this one by heart. Now, of course, you can always get by simply keeping a cheat sheet off to the side, and if I want to know what the sine of 150 degrees is, look at your cheat sheet unit circle. It's the y value because it's sine, and the y value is 1/2, so the sine of 150 is 1/2. But that's not going to work when it comes to an assessment because you don't get any cheat sheets. You're going to have to draw this from memory. The sooner you sit down and memorize this whole unit circle, the easier everything else is going to be. Everything else falls into place once you have this completely memorized. And memorizing doesn't mean knowing where to look it up. It means knowing it off the top of your head without really thinking all that much. Memorize, 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 memorize. And for that matter, it really doesn't matter what you do in the rest of this lesson until you have this memorized. So I'm going to go ahead and cut it off right here. We'll pick up next time with evaluating using the unit circle, but do not attempt that lesson until you have this unit circle memorized. It's a waste of your time to look at the next lesson if you don't have the unit circle memorized. So take a break, memorize the unit circle, and then take a look at the next lesson, evaluating using the unit circle.